So a lot of people who live nearby are electrosensitives and.
Okay, let's do the discussions and we are on
I
time.
have thoughts on this, let's talk later.
Okay. Oh, perfect, that'd be great, actually.
All right, hello, everyone. Good afternoon. We are on time for another exciting seminar today. Our today's speaker, I would like to request Dr. Joris Purvius to introduce.
All right, hello everyone. So this is Jacob Turner. Jacob works in the field of radio astronomy, observes pulsars and their scintillation. His history with this, notwithstanding his very young age, goes back a fair while. He started in Oberlin College back in Ohio about 10 years ago, working with the semi-legendary Dan Steinbring. After that, he went on to West Virginia University, where in Morgantown, West Virginia, where he did his PhD under Maura McLaughlin. And as of a year and 1 week from ago, he took up a postdoctoral position in Green Bank Observatory, where he's currently the only pulsar astronomer on staff, which means that he himself is basically responsible for like a third of the telescope time. So lots of responsibility on his shoulders. And he'll tell us some of the exciting stuff that's been happening with relation to scintillation of pulsars there. Thank you, Jason. Take it away.
Thank you for that humorous and very thoughtful introduction. Yeah, so I'm Jacob. I study pulsars and how we can use them to study the interstellar medium. And I'm going to be talking about an exciting new technique in the field of pulsar astronomy and how we can use that to further understand the interstellar medium and perhaps benefit other pulsar adjacent fields of study. So briefly, I'm going to describe what a pulsar is. So these are the remnant cores of stars that were typically in the 8 to 20 solar mass range. And these cores, when the supernova occurs, get compressed into an area around 10 kilometers across. They're about a solar mass in mass. And in accordance with angular momentum conservation, they have rotational periods, at least in this initial form, on the order of seconds to maybe a few tens of seconds. And there are scenarios in which if these pulsars already form and they're in a binary system with some other star that has left its main sequence, well, that star, if it comes under significant gravitational influence from the pulsar, will overflow its Roche lobe, begin accreting mass onto that pulsar. And again, in accordance with angular momentum conservation, the pulsar will spin up even further, in this case, to somewhere in the millisecond-ish range. And so we have two general populations of pulsars, one which are the canonical pulsars, which are formed from these supernovae, and then the millisecond pulsars, which are formed in this binary setup. And in this case, what typically happens if the system is not interrupted during this accretion process is we're left with a millisecond pulsar and a white dwarf companion, which is the remnant of that initial star. And there we go. And these are also extremely magnetic objects. Their magnetic fields are around 1 trillion times that of Earth. And electrons and positrons in the vicinity of these stars are accelerated along these field lines. And in particular, there's this emission mechanism that results in these radio beams, which is not fully understood, but a very oversimplified explanation is that these electrons and positrons are accelerated along these open field lines. And in this event, they emit coherent radio emission. And that's when we get these beams of radiation. And if, as is often the case, the magnetic field axis and the rotation axis is misaligned, and the magnetic field axis sweeps across our field of view, we will observe these beams in a sort of a sweeping pulse motion, not unlike that of a lighthouse. And that's where we get the name pulsar. It's just short for pulsating star. Now, these are absolutely incredible laboratories in space that can be used for all sorts of exciting fields of study that range from time and precision to testing gravity to observing the interstellar medium. And that is what I primarily focus on. So in particular, I focus on the ionized interstellar medium. And this, as the name suggests, is the region of our galaxy that is almost chiefly free protons and electrons. And these are regions that have electron number densities on the order of around 0.03 per cubic centimeter. This is just an H-alpha map that I pulled from the Wisconsin H-alpha mapper Northern Sky Survey, just to illustrate that this is a pretty bright region as far as line of sight of the ISM goes. this, everything that's in the wider range of this region has higher concentrations of H alpha, which is a generally good tracer for ionized ISM. And you can see that there's just a lot of structure that remains to be studied. And again, this is a full, full out view of the galaxy. But what pulsars are useful for is probing the smaller scale structure of this ISM, typically in the astronomical unit to parsec scale sort of range. And I will discuss how we actually do that right now. So this is a fairly oversimplified description of how pulsar emission propagates through the ISM. But I sort of want to take you on a journey briefly to of a photon as it leaves the pulsar, passes through the ISM, and then enters our telescopes. So when the emission leaves the pulsar, it is coherent, and that's really important because that means the phase information is retained in the photons, and that's crucial for analyzing the data at our telescopes. But a very simplified version of this is that it leaves the pulsar, passes through the vacuum of space, and then somewhere along the line of sight interacts with this thin screen of turbulent plasma. And when this happens, you're going from a medium with one refractive index to another. And so your propagation path is going to change. You're going to have scattering at some angle. You can also think of this as the emission undergoing a shift in phase. And because we have multipath propagation, the pulsar is emitting in many directions, right? Because it's spinning. And so we have photons entering this screen at many angles. And so we have phase shifts of different quantities. And so after this screen, we have these waveforms that are out of phase and distorted. And when all these out of phase photons combine and we visualize the results at our telescopes, we have this interference pattern. And tracking this interference pattern over frequency and time, observing frequency and time, is one way to visualize the structure of the ISM along these lines of sight. And we view these through what are called pulsar dynamic spectra. So this is I think a pretty solid example of what a dynamic spectrum of good quality data looks like. We have observing frequency on the y-axis, time on the x-axis, and I want to draw your attention to these bright patches right here. These are called scintilles, and basically they represent regions of constructive interference between photons on the various multipath scattering, and the darker regions are destructive interference. And it turns out that the decorrelation widths of these structures can actually provide a lot of insight into the structure and the behavior of the interstellar medium along the line of sight to these pulsars. I primarily study actually what happens when we take the two-dimensional Fourier transform of these structures, which results in a lot of cases in these parabolic arcs in what's known as the secondary spectrum. And so we have the conjugate frequency and conjugate time axes here. And what I want to draw your attention to first is that this is symmetric, and that's just because we're taking the Fourier transform of a real valued function. But these arcs are basically the best evidence we have that most of the scattering seems to at least occur at highly localized regions along the propagation path, and that's where we get this thin screen model. There's more recent evidence that may throw that thin screen approximation out the window a little bit, but still, a lot of the scattering seems to occur in localized regions along the propagation path. You'll also notice these arclet structures, which I won't get into detail about unless we have time at the end / if you want more information. But the general idea behind how these arcs form is as follows. So if you have your axes in your secondary spectrum here, let's say we have some photons traveling along the line of sight, and a photon scattering at some angle theta. So you'd have some interference between those photons, and that will result at some point in the secondary spectrum, let's say over here. And then if you have some and you have some photon that's scattered at a smaller angle theta 2, the interference between that photon and a line of sight photon will result in some signal further down the secondary spectrum, but you're starting to see an arc type structure maybe build up. But then if you repeat this interference between scattered photons and line of sight photons over many scattered photons, you start to build up this overall arc structure from photons that are being scattered both behind the direction of the pulsar's motion and in front of the direction of the pulsar's motion. And you get these arc structures. And the actual curvature of these arcs actually tells us where along the line of sight the screen is located. And some features like substructures in the arcs, like if they're patchy, may indicate that the scattering screens have astronomical unit scale inhomogeneities, for example. But one of the big questions in my field is what these screens are associated with. Now, some arcs have really obvious sources. So these are a couple of millisecond pulsars. J1643 -1224 is a pretty well-known one, but it is well known to be behind an H2 region. And the way you actually track where the screen distance is through basically MCMC on a time series that accounts for a bunch of parameters here, which I won't go into detail of. Basically, the idea is that when you account for the motion of the of the Earth around the sun, which will result in a slight change in the screen distance, and if the pulsar has a companion like a white dwarf, that might also alter the screen distance. And you track that over many months and years, you can actually constrain where along the line of sight these screens are. And in the case of this particular pulsar, we can say, okay, this screen coincides basically perfectly with where this H2 region is. And that in turn with the structure of the arcs can help us constrain, can help us obtain information about the scattering screen and what makes up the screen and how it's changing over time. But in some cases, it's not entirely clear. So this is a secondary spectrum of the closest and brightest millisecond pulsar, it's Earth, J0437 -4715. And what I really want to draw your attention to is just the sheer multitude of arcs that this pulsar has. So we have 26 known arcs. Some are associated with a bow shock near the pulsar, but most of them are just all throughout the propagation path of the photons from this pulsar to our telescopes. And that means we have a scattering screen once every like 6 parsecs or so. And that really is kind of confusing because, there's not really anything obvious along the line of sight of this pulsar, aside from maybe hydrogen filaments. And so we don't really have any obvious answer for what is causing all of these screens. There could be a bias just based on how bright it is and how close it is, but we'll get to that maybe in a little bit. So there have been attempts to sort of map all of these known screens in local pulsars with obvious structures. I may go into this if we have more time, but basically all these stick structures are the lines of sight to various pulsars. These black squares are known scattering screens, and all these other features are known structures. Like we have the local bubble here, we have molecular clouds. There's a couple of H2 regions somewhere in there. But the main takeaway I want you to get from this plot is that most of these screens aren't associated with any of these obvious structures. And so one of what I think is the most important goals of this field of pulsar scintillometry is obtaining as many lines of sight to the ISM as possible and trying to constrain where or what obvious structures may be associated with these scattering screens. And obviously it's difficult to obtain time for many pulsars for long periods of time in most individual campaigns, but that's sort of where I think efforts like pulsar timing arrays can come into play. Now, pulsar timing arrays are not designed for studies of the interstellar medium. I'm going to briefly go into what they're actually used for, but I think they could be valuable tools for studying the interstellar medium. So I'm a member of this collaboration, NanoGrav, which is the North American Nanohertz Observatory for Gravitational Waves. And the main idea behind this collaboration is to search for gravitational waves using observations of pulsars. Now, pulsars, especially millisecond pulsars, are very precise timers. In many cases, we can get down to sub-microsecond timing precision on these sources. And the idea is that if you have a lot of these, and you have in some distant set of galaxies, you'll have some merger of these galaxies, and at the center of these galaxies is going to be supermassive black holes that are also in the process of merging. And when they are in the process of merging, they create distortions in space-time known as gravitational waves. And as these gravitational waves leave the system, it will propagate out in all directions. I'm going to zoom forward a little bit. And some of these gravitational waves will inevitably reach our own galaxy. And as they pass between us and the pulsars we're observing, they will stretch and squeeze the space between us and these pulsars and cause the signal over many months and years to arrive sooner or later than expected. And assuming you can mitigate all the sources of timing noise in these systems, you can recover the signals chiefly caused by the perturbations in space-time from these gravitational waves. And many pulsar timing arrays in the past year or two have announced 3 to 4 sigma detections of a stochastic gravitational wave background of gravitational waves formed from the combined signals of many supermassive black hole mergers from all over the universe. But we want to further probe these perturbations, and that means an increase in timing precision is necessary. So that's sort of the main goal of pulsar timing arrays, but these also can be used for studies of the ISM, partially because we observe many pulsars on a high cadence. So we observe pulsars on the order of like once every couple of weeks to once a month. And we have tons of lines of sight, which means many views to the interstellar medium. Nanograv, I think, times at least 70 pulsars at this point. And because we have many years of data, we can constrain screen distances over long observing baselines and get high precision of these distances to these screens. But there are a couple of detractors, at least in the traditional observing setups that are done, which means that, or which chiefly of which is because by nature of their efforts, timing arrays prioritize timing, and so they necessarily sacrifice frequency resolution in prioritization of this timing resolution, which is an uncertainty relation known as the Gabor limit. These scintillation structures are dependent on resolving scintills as far as constraining the ISM structure, and the most highly scattered pulsars have the narrowest scintills. And so if you don't have the frequency resolution to resolve those scintills, you can't do much in the way of ISM studies. And I would argue that those are the most scientifically interesting lines of sight to study. And so in this current setup, that's not really feasible. Now, what you could do is just take baseband raw voltage data off these telescopes and then process them with the prioritization of high frequency or high time resolution for your own personal interests. But baseband data is very storage intensive, and for reference, for some baseband observations I'm running myself, 2.5 hours of observations on the Green Bank telescope is about 25 terabytes of data. And if you have 70 pulsars with 15 years of data each, and you're observing once a month, storage of this kind of data is not practical. And so there needs to be workarounds to make ISM studies with this setup actually work. So I propose using this technique called cyclic spectroscopy to get around the issues of improving noise in pulsar timing arrays and using pulsar timing arrays to study the interstellar medium. So the nice thing about pulsars is that they actually have a periodic signal, which is pretty unique as far as naturally occurring emission from anywhere in space goes. And because of that, we can actually utilize information contained within the higher harmonics of these signals by recovering both amplitude and phase information, which is really unique because most forms of spectroscopy only focus on amplitude information. And amplitude and phase allows you to do a lot more stuff with your data than is otherwise possible. And I claim that this technique can benefit both efforts in pulsar timing arrays and studies of the interstellar medium simultaneously. And I'll briefly go into how that is done. But first, I want to discuss what a cyclic spectrum is and how is it formed. This is the only intensive math on my slides, I promise. So the basic idea with a cyclic spectrum is for some electric field, you're going to have information at various observing frequencies nu, and you're going to have information in the higher harmonics of that signal, which we're going to represent with this alpha parameter. And alpha sub k is equal to k over p, where k is your harmonic and p is your period. So basically, we're dealing with integer harmonics of your inverse pulse period. And your cyclic spectrum is formed by taking your signal at a given frequency, shifting it by half of your integer inverse harmonic, and then multiplying that by the complex conjugate of your signal shifted in the opposite direction. And for pulsar specifically, you can write this as your transfer function of your interstellar medium and the intrinsic pulse shape itself, which is this S sub x parameter. And when you combine all that together, you get something like this, where you have radio frequency on the y-axis and cyclic frequency or harmonic on your x-axis. And I'm showing this plot chiefly to illustrate just how much information you can extract from your data if you take advantage of the higher harmonics of your signal. So you can see in this particular example, we have information out to like the 30th or maybe even 40th harmonic of your signal, which is a lot of information that's not utilized if you just care about your standard non-frequency shifted signal. And this is dependent on the duty cycle of your pulsar, or your signal in general. But suffice to say, for millisecond pulsars, there's a lot of information out to the 30th or 40th or 50th harmonic that is not utilized with conventional observing techniques. So now the question is, how can this benefit pulsar timing arrays? So it turns out that delays from interstellar scattering are one of the largest sources of uncorrected noise in pulsar timing arrays. And I'll get to why we don't currently correct for it in a second. So most pulsars in nanograv, for example, have timing noise on the order of hundreds of nanoseconds to maybe a few microseconds. And it turns out that in the higher frequency data we observe, we see timing delays from scattering, or this when we monitor timing delays for scattering, we see that they're on the order of tens to hundreds of nanoseconds, meaning that, in conjunction with our knowledge of the RMS noise in most pulsars, if we can mitigate these scattering delays, we can noticeably increase our sensitivity to gravitational waves. And what I'm showing here are various time series of inferred scattering delay on top. This is 0 to 20, 0 to 50, 0 to 50, 0 to 10 nanoseconds of delay. And this is just flux density and dispersion measure. But what I want you to take away from this is that scattering delays are persistent, but they're also changing. And that's important. So scattering over reasonable timescales is a stationary random process. And that means that simply assuming a sort of characteristic scattering delay for a given observation and just going with that for decades in the future might not be your smartest choice, even if it is efficient and easy, because epoch to epoch variations in these delays could significantly change the timing noise of a given epoch. And so you want to be able to correct for these per observation rather than just on average. Now, the way that this is done typically, this estimation, is by taking your dynamic spectrum that we have up here, finding the two-dimensional autocorrelation function of this spectrum, and then finding the one-dimensional autocorrelation function of that along your frequency lag. And then once you do that, you fit the characteristic width of this frequency lag, which is just the characteristic width of any given scintilla in frequency space, which is known as the scintillation bandwidth. And from there, you can approximate your scattering delay tau from your scintillation bandwidth delta nu d using this equation. However, there's some factors in this that are not known a priori, namely the scintillation constant C1, which you could just assume is 1.16, which would be consistent with the Kolmogorov medium. But the problem is not all lines of sight seem to follow that turbulence behavior, and it can vary from around 0.6 to 1.5, meaning that your estimation of scattering delay can be vastly different depending on your line of sight. And this is really important because if we want to properly correct for these delays, we want to understand the medium sufficiently. And in this context, that doesn't really work very well. And again, I mentioned before, because we prioritize frequency resolution, this only works for pulsars in which scintillas are resolvable in PTAs, which means that the pulsars with the highest scattering, i.e. the ones that we want to correct for, are not correctable because we can't resolve their scintillas. And also another important thing is dynamic spectra only utilize the amplitude information in your signal. So to get around this, we turn to the actual intrinsic pulses themselves. So as I mentioned before, pulsars, multipath propagation causes scattering when the emission interacts with the turbulent plasma, but this also results in an angular broadening of the signal. And as a consequence of that, your actual observed pulsar signal is going to smear out in phase. And I'm illustrating that here with lower frequency observations in the bottom, higher frequency observations in the top. And the takeaway here is that as you observe at lower and lower frequencies, the effect from scattering sufficiently smears out your signal. So you can think of your pulsar signal in conjunction with the ISM signal that you observe as a convolution of basically a Gaussian structure and a one-sided exponential, which is generally what we assume the ISM follows as far as the scattering that's imparted onto the signal. And if we could use this information, then we have a direct method of measuring scattering because we have amplitude and phase information, as opposed to the amplitude only information of the dynamic spectrum. And it turns out that you can do this with cyclic spectroscopy. I'd be happy to go into the math later on, but just trust me when I say that cyclic spectroscopy can perform a deconvolution of this impulse response function from the intrinsic pulse. Example here is on the top, we have a recovered impulse response function. In solid black, we have the recovered intrinsic pulse, and in dashed black, we have the signal that was observed at the telescopes. And note the scattering tail that was in the signal that was observed, whereas there's no such tail in the recovered intrinsic pulse. And the reason this pulse has multiple components is that this pulsar in particular is very edge-on to our telescopes, wherein we see one side of the beam, and then we also see the other pole of the pulsar pointing almost directly at us. And I'm happy to go into the math of this deconvolution if you want, but just trust me when I say this can be done with 6-spec. And not only that, but it turns out that if we we can run simulations to determine whether or not this technique is equal to or better than the estimation technique using autocorrelation functions. And we can do that through simulations of scattered pulses, wherein we recover the injected delays using this autocorrelation function technique versus attempting to recover the impulse response function using cyclic spectroscopy. And if we do this over many iterations, we see scatter plots like this, where we have injected scattering delay on the x-axis and recovered scattering delay on the y-axis using different approaches. This approach fits a Lorentzian to the ACF, whereas this approach uses the cyclic spectrum to recover the scattering delays. I do want to mention the reason we use a Lorentzian fit is because in frequency space, in the time domain, your one-sided exponential is the signal we see that imparts scattering onto the pulse. But when you Fourier transform that into the frequency domain, you get a Lorentzian, and so that's why we fit Lorentzians to the ACF in frequency space. But the main takeaways I want to make for these figures are that the precision and accuracy of this cyclic spectrum technique is far better than the ACF technique. And not only that, but the correlation between injected and recovered delays for the cyclic spectrum technique is also far greater. And I mentioned before, we really care about the epoch-to-epoch variations in scattering. And so this correlation really sort of emphasizes how much better this cyclic spectrum technique is than the dynamic spectrum ACF approach. So that's how PTAs can benefit from this. But I'm an ISM astronomer, so this is cool. But I want to focus the rest of the talk on how this can actually benefit studies of the interstellar medium. And this is where I really start to get into regions where I need to be careful because I get overly excited with the results of this. No problem. But the main thing I like about cyclic spectroscopy is that for periodic signals, you can actually bypass this Gabor limit and improve frequency resolution without sacrificing time resolution. And the way this is done is, again, by resampling your data at integer multiples of your inverse pulse period. And this can be done up to scattering delays equivalent to half of your pulse period. And the results of this, I think, are really spectacular. This is my favorite plot to show in talks, just because I think it's kind of drawing the difference between these two figures. But what I'm showing here are dynamic spectra of a really highly scattered pulsar, B1937 plus 21, processed using the typical pulsar timing array observing setup and using cyclic spectroscopy. And in the typical pulsar timing array observing setup, you're limited to frequency resolution of about 1.5 megahertz. And what that gets you typically is, you can obviously see there's some sort of scintillation structure, but it's not really clear what that scintillation structure is. You can just tell it's there. But if you process this data using cyclic spectroscopy, all of a sudden you get this fantastic scintillation structure all throughout your spectrum. The scintillas are bright and vibrant and beautiful. And there's all sorts of valuable information that is now available for studies of the interstellar medium. And when you get scintillation, you can also get scintillation arcs. So these are the same images from the previous slide, but Fourier transformed to look for scintillation arcs in the secondary spectrum. And what I really want to focus on is the extreme difference in the y-axes here. So these y-axes represent the differential Doppler delay of your signal, where higher up the delay axis means the photons were scattered at a larger angle at the screen to get to our telescopes. And I want to make a point to mention that there is over a 2 order of magnitude difference in the y-axes of these plots. And actually, this figure goes up a factor of 4 higher. I just cut it off because there's only a signal up to around 12.5 microseconds. But this is a consequence of your improved Nyquist limit in your observations. And the idea with that is that with higher frequency resolution, your Nyquist limit drastically improves. And I don't think I mentioned this, but the difference in frequency resolution between the left-hand side and the right-hand side is 256. So this side has 1.5 megahertz channels in frequency. This side has 6.1 kilohertz channels in frequency. So it's a huge improvement in the resolution that's possible. And what this results in is all the information on this side is constrained to the tiny region of the origin on the right-hand side. So you can't even see the scintillation arc structure with the typical resolution that we have for this particular pulsar, much less the additional features that expand further and further up the delay axis. And I briefly want to compare some of these results, which are in this viridis color scheme, to previous cyclic spectroscopy observations in black and white taken at lower frequencies. And I want to mention these data are 6 years apart, which is really interesting because a lot of features like these arc-like structures still persist across these many years, which tells us that the ISMs of this pulsar, while obviously changing over time in some respect, is still providing more or less the same scattering screen, which is really interesting. And again, I want to mention the difference in the y-axis, but sort of in the opposite direction, so to speak, wherein there is a factor of 2 difference this time between, or actually, I guess a factor of 1.5 difference this time between our figures and the secondary spectra of these older observations. But rather than being a detractor, this time it's actually a benefit because all the information, all the fine structure and all the arc information in our data is now constrained to this fuzzy unresolved feature at the center of this secondary spectrum. So in this respect, we can not only resolve structures in our scintillation arcs, we can actually probe smaller angular scales as well. In fact, the angular scale difference we can probe between these 2 figures and this figure in the center is a factor of 6 to 10, which is really quite interesting. So these studies can be complementary, is what I'm trying to get at. So I and a team of scientists and engineers at the Green Bank Observatory are currently working on a cyclic spectroscopy backend. And the idea behind this is that if this technique is performed in real time or near real time, you can acquire this simultaneous high time and frequency resolution without the need to store your baseband data that would be required to process this 6-spec approach otherwise. And so what I'm showing here are just examples of test observations using this backend. So we have high quality cyclic spectra. This periodic spectrum is just the Fourier transform of this, and we can already recover impulse response functions and fit their corresponding delays using this test data, which is really exciting. And so this will allow for pulsar timing arrays like nanograv to not only measure scattering delays sufficiently on individual epochs, but also will allow us to probe the ISM across 70 plus arms throughout the galaxy and result in unprecedented and highly detailed studies of the interstellar medium. For those of you that are in the room that are maybe interested in pulsar studies and looking at Eurus, we are hoping to make this available in the 2025B or 25B or 26A observing semesters. So be on the lookout for that in the next couple of months whenever we announce that officially. I have time for questions, but thank you for your attention.
All right, any questions?
Yeah.
I think Sonny's first.
Wait, could you go back to the slide where you show the pulses getting smeared out at lower frequencies?
Yeah, yeah,
Yeah, that one. Okay, so I guess you're basically assuming the intrinsic pulse shape is independent of frequency.
there is some frequency evolution as well.
Okay, yeah, that was my question. It's like, how do you know that?
Right, so, the way cyclic spectroscopy typically, deconvolves your signal is it makes some assumption about the intrinsic pulse, but the way you actually feed information into the pipeline that processes this is you observe the pulsar over a, certain number of minutes or hours to build up signal to noise. And from there you can create a pulse template that is then used for the deconvolution process. And the deconvolution process, yes, does assume, actually primarily assumes information about what the actual impulse response function is, more so than the actual intrinsic pulse. And so the deconvolution assumes something like a one-sided exponential. And from there, you deconvolve your signal. Now, the frequency evolution is also really important for this because we want to do this at relatively discrete ranges in frequency space and over discrete timescales. So for a pulsar like this, which is incredibly smeared out, you may want to limit your frequency range over which your data is fed into this pipeline into, say, I guess in this case, like 100 megahertz samples or sections, and then you develop your own recovered impulse response function for each of these individual sampled pulses, or I guess sampled, because each of these are not individual pulses in this case. They are pulse profiles that are integrated up over observations of minutes to hours, for example. Individual pulses are pretty low signal to noise in most cases. So you assume some sort of stationarity and non-time variability of the pulse itself in order to form the template that you use for the deconvolution.
Right, great, yours?
Yeah, I had a very simple question. At some point you showed a dynamic spectrum on the top, autocorrelation function in the middle, and the bottom, the one I mentioned. Yeah.
Yeah.
So, the middle plot, the labeling of these axes, that's arbitrary, or is there a reason it's like this?
These axes?
Yeah,
So,
because I would expect 0, 0 to be in the middle.
oh, shoot. You're right. This is a typo. Thank you. You're absolutely right. Yeah, that's a typo. 0 should be in the middle. Thank you for catching that.
Yeah, no, I was just wondering if you
Yeah.
had a reason, but
No,
that's fair enough.
you're absolutely right. Yeah, this should be shifted over. Thank you. In the paper, it's correct. I double checked. Yeah, in the paper, it's correct. I know that. Because this, yeah.
The different thing that was a bit unclear to me was you show the Dumorez 2011 deconvolute. Yeah, that one. In that bottom plot,
Yes.
the dashed lines, they've been manually shifted to align with the full lines, because this is not what scattered pulse wave looks like. There's supposed to be a phase delay, right?
Yes, you're absolutely right. And I'm guessing that's what's showing here. I'm guessing that's
Okay.
what's being shown here. But yeah, you're right. Yeah, in reality, the observed signal, the peaks of these two, of the pulse and the interpulse would be shifted a little bit in phase. That's right.
Okay, thanks. That 10 minutes clear to me. Thanks.
All right, great. Any other questions? Go ahead.
I have a very basic question, I think, but I wonder, this is from the very beginning when you were explaining what a pulsar is,
Mhm.
and you have the rotational axis and the magnetic axis.
Mhm.
And I wonder if if the center of both are completely like aligned with the, if there is any way to know or not.
I mean, so if that was
And
the case.
I can tell you why I'm asking that.
So if that was the case, you would either not see the signal at all because it wouldn't be aligned with our line of sight, or you would just see or I guess you wouldn't see a pulse, you'd see a constant signal that maybe fluctuates with time with scintillation.
No, but what I
Sure.
yeah.
I think, are you asking, is the center of the magnetic axis aligned with the center of the like the center of mass?
Yes.
rotation?
Yes,
So does the magnetic axis actually go
Because-
through the center of
Oh,
mass?
no, no,
Oh,
Yes,
I see,
because- in Uranus and Neptune, in both planets, it is not that way. Like
Oh, interesting.
the axis of the magnetic field, the
Mhm.
center is shifted
I
to
see.
one side of the
So
planet.
would that result in some sort of precession then?
I have
Or,
no idea.
Okay.
Actually, I think
Okay.
it's not known why.
okay,
Mm,
oh, that's interesting.
Yeah, I remember
this-
that. I have no idea if anyone knows what pulses is.
I remember studying that in the university
Mhm.
years ago, and it was always curious to me. And now when you about, and I mean, I knew what a pulsar is from a long time ago too, but it came to my mind. I don't know why it connected with my mind.
That's a really
And
cool idea. I'd have to ask.
yeah. I wonder if we can actually measure that in pulsars.
I would have to ask, you would have to ask people that specialize in the emission mechanism of the pulsar. I wonder if maybe we can learn about this from polarization calibration studies, but that's not my area of expertise, unfortunately. But that's an interesting idea. I'll have to bring that up with my colleagues. Thank you for that.
No?
Yeah, I suspect, if I may, I suspect polarization would be the way to probe this.
Mhm.
However, we also know, especially for the MSPs, which is mostly what we've been talking about. We know that it's not really a dipolar magnetic field anyway. NICER has, in the last couple of years, made some really nice results where they actually imaged the emission regions, and they show that in some cases you just have some really complex multipolar magnetic field, which means it becomes a bit of an irrelevant question at that point.
Okay.
Which is because these things spin so quickly that for the surrounding plasma to co-rotate doesn't really work because it needs to go beyond the line of sight. Beyond the speed of light really quickly, and that's why it all gets deformed.
So it's not just a dipole, like what harmonics you actually need to describe it.
idea.
Okay.
I have no idea.
How high does it go?
All right, any questions from the online participants? Please unmute yourself or type in. All right, looks like there are no questions there. Okay, let's thank our speaker again. Yeah, we'll end the presentation here today, but discussion will continue.